So I forgot to record this earlier. Let's go back to here for a second. So we're just going to, aqueous solution is water. Water is the solution, yes. Aqueous solution, water is the solvent, I should say. Electrolytes are conductive. Ionic compounds, acids are conductive. Molecular compounds are non-electrolytes. They should not conduct. We'll talk about that in a second. I just asked the question, does pure water, or does water conduct? If you drink this stuff out of the water fountain, does it taste like, it tastes funny, doesn't it? I think it does, okay? That taste that you're tasting is probably a little bit of iron, okay, from the water. It's just, that's natural, it's minerals, okay? But it kind of tastes, nah, you know? It doesn't, it's fine, okay? There's probably some copper from the pipes in there. There's probably some ions that are floating around in there, okay? And yes, it would be conductive for sure. If you took pure distilled water, if you go to Sobeys, okay, or the water that we use here is okay. Okay, I'm going to be perfectly honest. It's okay. We used to have a filtration device, but it kept leaking all the time, so we just got rid of it. We don't use it anymore. We use a different water system now. But the water that I have in here is probably going to be not great because, first of all, I did not clean the beaker. Okay, so it's probably going to conduct. Hopefully not a lot, but it's last class it was 5 out of 10, which is not good. Okay, it should be 0. If you clean it out really well and rinse it out really well and you use some proper distilled water, again, I don't know how clean these bottles are either. If you use some proper distilled water, it should be 1 or 0. Okay, pure water, we're going to talk about this. This is where pH actually comes from. So when we talk about pH scale, it actually comes from pure water. So we're going to talk a little bit about that. Water's pretty unique. Water is a pretty special thing for us, that's for sure. Not only is it polar and all that other good stuff, and helps dissolve things and whatnot, but it's actually, like I said, pretty unique compound. This should be 0, maybe 1 at most. Okay. This is before I put anything in here, so let's take a look here, and it's already a 3, 4. Okay, so it's going to be somewhat conductive. My point is this. So it's a 3, 4 already. If I put some sugar into here, okay, and I stir it up, I'm just going to dissolve this here. By the way, sugar is polar. Would you agree? C12H22O11, probably polar-ish, yeah, at some point anyway. Water's polar, so this dissolves pretty easily. Okay, that's kind of the key to what dissolves in a molecular compound. It's polar, water's polar, negative ends attract positive ends, etc., and they tend to dissolve fairly easily. If you take a non-polar liquid, like cooking oil, for example, we talked about this a little bit in Unit 1. If you took cooking oil and put it in here, you know what happens when you put cooking oil into water, right? You've done that before when you're cooking noodles, right? When you're cooking noodles, you put a little bit of cooking oil in there just so they don't stick, yes? Or whatever, yes. It does not dissolve, right? It sits on the top and kind of just sits there, right? And of course you boil them so it kind of mixes up a little bit, but it doesn't really dissolve because, again, cooking oil is non-polar, water's polar, there's no negative and positive. That's kind of what decides if it's going to dissolve or not in water, okay? Good enough. But you can see it's kind of dissolved now, yes? I don't think there's a little bit at the bottom, but I'm not going to spend any more time on that. And again, supposedly this should probably be exactly the same as it was before, because molecular compounds don't have any ions, right? There's no pluses and minuses. So this should be the same 3, 4 as it was before, okay? And yeah, it's about a 3, okay, in this case. So it hasn't really changed, okay? In that case there. And again, this would be exactly the same thing if I had a clean beaker and all that stuff, it'd probably be 0, maybe 1. It depends, okay, on that. And we'll talk a little bit about that. So I'm going to leave that over there, okay? Yeah, I don't know what's in there. That's a problem. Okay, anyway. Good, yeah? That's called separation. Separation is the term we give for molecular compounds, which that was, okay? The next one we're going to talk about here, by the way, that's right here somewhere. Where's that? Right here. Separation. So these molecules of sugar that were all linked together are now individual molecules of sugar. If you drank that beaker, it would still taste like sugar, right? Sugar water. because you get individual molecules of sugar that are spread throughout the solution. Okay? That's separation. It shouldn't conduct electricity. It technically didn't because we started at 3,4. We ended up at 3. Okay? So it didn't increase the conductivity, that's for sure. Okay? Dissociation is next, and that's for ionic compounds. And I'm going to skip this one for right now because that's my demonstration today. But ionic compounds. And when I put an ionic compound into water, one of two things is going to happen. It's going to break up very easily, or it's not going to break up very easily, but it's going to break up to some extent. Okay? To some degree, it's going to break up. How much? It really depends on this, which you're going to get out for me today, which is called the periodic table. Yes? So let's get the periodic tables out there, and backside is what we want. Maybe. Okay, maybe not. Oh, it's locked up, is it? I don't know. Let's see if I can do it over here. Okay. I see. Okay, well that's thinking. Let's do this. This one, I guess. There. And we're looking for. We're going to look for this right here, of course. Okay, and this is what we call the solubility chart. Yes. Okay. So solubility chart, of course, this usually kind of tells us how well these ionic compounds break up. And this is called aqueous right here is another term for this. And you might want to put that in there. Very soluble implies that it's aqueous. Okay. AQ. And these are usually what we call the precipitates, if you remember, the solids. And so we're going to use this today, and we're going to show you what's happening with these ionic compounds when we put them into water and what's actually taking place. Okay? Now, going back to here for a second, dissociation, we're going to talk a little bit about that. That's actually what we're focusing on today, is dissociation. And that's a big part of what we're going to be talking about in this unit, actually. And, of course, dissociation is for ionic compounds. Ionic compounds should be conductive in a solution. Okay? So we should get some conductivity here with that, okay? Because there's ions that are present, of course. And ionization is, of course, the term we use for acids. I didn't bring any acids to investigate today. We'll do that at another time. But ionization is the term we give to acids, okay? What we're going to talk about today here is, just don't look here. I'll get rid of this. We're going to talk a little bit about what we call selective precipitation, or basically just what's happening when we put ionic compounds into water, okay? And there's a couple things that, there's not a lot to do today, but you definitely I just want you to pay attention. Obviously ask if you got any questions to see what's going on, or if you don't understand, that's fine. But there is some things that I need you to kind of understand from today's lesson, so that going forward you understand what happens when we place ionic compounds into water. And really, in this case here, by the way, speaking of this is a Science 10 thing that we did probably, and I know that was a long time ago perhaps, but does anybody remember what kind of equation this is? What kind of equation is that? Yeah? No. That's an option, not the right one. No. Double replacement is correct. Okay? So this is a double replacement reaction. It's double replacement because it's two ionic compounds mixed together. Okay? Do you remember when we talk about double replacement reactions? Okay, look at this equation. What do we tell you happens? How do you figure out the products? If I didn't have these here, for example, let's say you didn't see this in here, and I said, and this is, by the way, what we're going to do in Unit 4. We're going to look at the 5 reaction types again, which are what? Formation, decomp, yeah, combustion, you said, single replacement, and double replacement. We're going to look at those 5 again, and that's what we're doing in Unit 4. But Do you remember how to predict what the products are? What do you do here? You switch the, we tell you to do what? Switch the metals, yes? Right? Switch the metals, okay? So we tell you to do that. What's actually happening here, I'm going to show you today. Let's take a look at that. So let's get rid of that for a second, and let's go down here, and I'm just going to show you some stuff here. Just give me a second. And we're going to get you to draw. This is on the back part of lesson 1. Back part of lesson 1. And let's take a look at what's happening here. Okay? Now, here we go. Okay? So I'm going to take some lead-2 nitrate, it says here, and it's called aqueous. Okay? Aqueous means that this lead-2 nitrate, by the way, what state is lead-2 nitrate in to start with? Lead-2 nitrate. What kind of compound is that? Ionic, so it's in what state? Ionic compounds are always in what state? Come on. Solid, okay? So we're going to start out with a solid, and I'm going to put it into a beaker of water. When I put it into a beaker of water, okay, one of two things is going to happen. And those two things are right here. So we're going to go to this, and I'm going to say, okay, let's find lead-2 nitrate here. What kind of compound? Is this a very soluble compound, or kind of that one of those slightly soluble? Slightly soluble. Where's lead-2 nitrate? Here's nitrate right here, and O31 minus. We always, by the way, if you don't remember this, we always find a negative ion across the top, yes? So we always start with the negative one. In this case, nitrate is right there. Where's lead-2? Is it here, most, or do you see it here somewhere listed? Where's lead-2? Most or in the other part? Most, right? So lead-2 is here, okay? So lead-2 and nitrate basically means it's aqueous, right? What does that look like? What that means is this: it's very soluble. So when I put lead-2 nitrate into water, it should probably be very soluble. It should break up very easily. Yes? Water is polar. It will attract the positive end, the negative ends, and pull this ionic compound apart. Okay? So if I was looking at this part here, I'd say what's probably going to happen is I'm going to get some lead-2 ions and some nitrate ions floating around in here. Okay? Kind of like that. Okay? And let's see if that in fact takes place here. So here's some water. Okay. And I tried to do this last class, and I tried to use as little as possible. It didn't work out very well because we couldn't see anything. If you can actually see anything. So I'm going to put a little bit more in this one here. This one here is the lead-2 nitrate. It's solid. Yes? Oh, okay. I'm dancing here. I'm going to put some lead-2 nitrate. I was going to do this over there, but Kylie's here today, so thanks a lot. How much do you want me to put in here? Let's go with, can we go with that much? Okay. Huh? It'll do. There. How about that? Good? Okay, good. Lead-2 nitrate. So, but I don't know if this is all going to dissolve because it might be too much for the water, but we're going to put it in. Okay. Where can I put this now? Okay. So that's my lead-2 nitrate. I'm just going to mix that up here somewhere. And this apparently should dissolve if I have enough water. Obviously, sometimes it won't all dissolve because if you put too much in, there's not enough space in between. What's actually happening right now, by the way, actually I never talked about this in the first period or last period. What's actually happening is, remember, there's actually spaces between water molecules, yes? Right? In solid form there isn't, but in liquid form there is. And the lead-2 ions are going in between the spaces, and the nitrate ions are going in between the spaces of water right now. Okay? Now when the spaces get all used up, and there's no more room, I can't dissolve any more solid, yes? We call that saturation. Yeah? What? No. Okay. Okay, no problem.
Sounds like a plan.
So is that okay? Good enough? Yes?
Yeah.
It's pretty much all gone. There's a few little grains at the bottom there, but for the most part, it's dissolved. Okay? That's because it's aqueous. It breaks up fairly easily. We obviously have enough water in this case for that to happen. Okay? I'm going to put this here. Okay? And now I'm going to take a look at potassium iodide. So I'm going to put this into a beaker as well. And again, it says that it says aqueous. Let's see. Iodide's here. Yes, there's iodide. We always look for the negative ion across the top. This is how we do solubility chart, and this is important. And then K+. Where's K+? Is it down here? Yes or no? So it's got to be here, yes? Most. So again, it should be very soluble. If I put potassium iodide into water, it should disappear. Basically very soluble. Again, assuming that I don't put too much in, right? Even if I did put too much in, there's still going to be a lot of ions. Oh, by the way, conductivity. Let's check the conductivity here. If there's in fact ions in here, this should be conductive, yes? Okay, what? No. And it is. Look, it's 7, yeah? So it's pretty conductive, yeah? Yeah, go. Yeah, go, you two. Hurry up, though. You're missing out. I'm telling you, I'm not repeating this. This is good stuff here, people. Okay, so let's do this with potassium iodide here. And here's potassium iodide. And again, let's use about that much. Okay, say about the same amount. Should be good there. Okay, and so I'll have to use this for okay, and this one actually breaks up even faster. Okay, and it's dissolved already. Yeah. Okay, so again, very soluble, aqueous, breaks up very easily. Now, what happens here is I'm going to stick it back there so I keep track of them. Now, what I'm going to do is, of course, I'm going to combine them together. Okay? So I'm going to put all these things together now. I'm going to pour these two together and make one big reaction here. Basically, I'm going to take this plus this and to give me this. So really what happens is I got this, and this, and this, and this, and some of this, and some of this. Yeah? So I have all these ions that are floating around in this solution. And when we get all these ions floating around here, of course, okay, what do you know about ionic compounds? Its opposites attract, yes? So again, well, first of all, is lead-2 going to be attracted to K+? Lead-2 plus K+, are they attracted to each other? No. Like charges, yes? So they're not going to be attracted to each other. What about NO3 and I-? Are they attracted to each other? No, they're both negatives. Okay, so that's not an option. What about, let's do this. Let's do, let's do K and I. Are these two ions attracted to each other? Are K pluses and I minuses attracted to each other? Positive, negative, yes. But we've already talked about that, and we said, hey, K plus and I minus are attracted to each other, but look, water is strong enough to break them apart, yes? They're very soluble. So they are attracted to each other, but water says, hey, you're going to stay apart from each other. And same thing with lead-2 and nitrate. Look, lead-2 is attracted to nitrate. Those are opposites. But again, water's decided already that, hey, you guys aren't going to stick together. Okay? What then that leaves us is, look, lead-2, is it attracted to I minus? Yeah, it's attracted. And so is K plus. Is K plus attracted to nitrate? Are those two attracted to each other? Yes, they are. Okay, so we get kind of what we have here is 4 ions, and now we're starting to match them up, right? So if I look at K plus and NO3 right here, we see that here's NO3 again right here, yes? And K plus is here, and again, very soluble, yes? So they're attracted to each other, but water's going to say, no, you need to stay apart. I'm going to break you guys apart. I can break you guys apart, so I'm going to keep you guys apart, and it's very soluble. So if I put potassium, if I went back and we have some potassium nitrate in the back room, okay? If I went and got and put in water, you see exactly what I showed you here. You wouldn't see anything because potassium ions and nitrate ions split apart. Okay, they split apart from each other. So you wouldn't see anything. But the last one here that I showed you is lead-2 and iodide. What happens when those two ions come together? This is where we get the slightly soluble option. Look, right here. Here's iodide, right? Iodide. And here's lead-2. Yes? Down there now, yeah? And what that means is, how do we indicate that is basically we say, hey, that's going to be a solid, or it's going to be slightly soluble. Okay? Now, is there going to be some free lead ions and some free iodide ions? Absolutely. Okay? But most of them will come together, and they come together and stick together. Okay? Water cannot break them apart as easily. And we're going to see that because when they come together, okay, they're going to stay together. And they form what we call, usually you can call the precipitate. Okay? And we can check that out. Okay? Now, I'm debating. Last class I did something different and it actually worked out a little bit better. So hopefully I'm going to maybe do that. Is that okay? I don't know. I think it's going to be better because I'm going to show you the two parts, I think. So I'm going to do that. I'm going to take this one here. This is the lead-2 nitrate. And I do have a solution of potassium iodide here. If you want me to add that later, I will. But is it okay if I just mix this one into this one? Is that okay? So just pretend like this. Look, this is a solution, yes? And I'm just going to put this into the solution. Now the solution already has, what was this again, lead-2 nitrate. I'm just going to add this potassium iodide to the solution, which basically means I'm going to add two solutions together. Is that okay? Is that okay? It's going to be the same. It's going to work out a little bit better here, I think. At least it did last time. I don't know. I can't promise anything here. Okay, so here we go. That should probably do it. Okay, so lead-2 nitrate, and here's some potassium iodide. And again, the first thing that's going to happen here is the potassium iodide is going to split apart into ions, because that's what it does. It's very soluble. And then the opposites are going to find each other, and I guess make this solid, supposedly. Okay, good? All right. Ready? Aiden, you ready? All right, here we go. Ready? Did you guys hear that all the sports are canceled? Hey, that sucks, eh? Yeah. No more. Yeah. Oh well. That kind of sucks. All right. Here we go.
So.
Now you got to watch closely because you might not see it, Taylor. You might not see this, Taylor, especially if you turn around. And I don't want you to miss out. Ready? Okay. I got another coffee today, by the way. So, yeah, I got.
Where'd you get it from?
Tim Hortons.
Ah.
Yeah. I think it was a large, medium.
Regular?
No, yeah, regular. 1 cream, 1 sugar. Huh? Not impartial. Don't matter. I like coffee. Sometimes it is a little too strong. If I don't eat enough food, I find that I get a sore tummy. Yeah. I get a sore tummy. All right. Oh, we're still recording, huh? Oh. Hey. All right.
Oh, what are your plans for the weekend?
Ah. What? What's going on right now? Okay, here we go. Ready?
Yes.
Okay. What?
Why?
Boom!
7 minutes for it to change.
Good. Questions, anyone? Okay. So now, what we need to talk about is a little bit of this. And this is the next part that I need you to understand here, and this is just as important as what we just finished talking about there. But I don't really care too much about the selective precipitation at this point, okay? But I do care about this part. If you wanted to test for, let's say, I have a beaker, and I want to know, does it have bromide ions in there or not? Let's just talk about that for a second. what could you add? Look at your periodic tables. What could you add to this solution to decide if bromide ions are in there? Obviously, we want to add something that we can see, right? So I want to add something. If this is Br minus, what do I want to add instead? I want to add a positive or a negative ion here. Positive. Which one do I want to add? Do I want to add something that's very soluble? Or do I want to add something that's maybe slightly soluble so I could see something happen? Slightly soluble. So when we look at our chart here, okay, here's my Br minus right here. It's actually in the same category, right? There's Br minus. What could I add? Well, you could add, for example, I don't know, whichever you want, but you could add any of those ions, right? Like maybe silver ions, for example. But here's the next thing I want you to understand. Let's say, we can write this in there, by the way, add some silver ions. Okay? That would check to see if there's bromide in there. Okay, now, there's a little issue with this, of course, you know, if you noticed on that chart, it also said chloride and iodide as well, so it could be any of those ions technically, but let's just go with that. What if let's go to this one, let's jump to here for real quick. What if I wanted to test for Mg2+, what could I add? So give me an option for that. What would I add to test for Mg2+? Yeah. Fluoride? Yeah, sure. Here's F minus, and here's my Mg2+, yeah? So I could probably add some fluoride. So let's write that down. Add fluoride. Okay? So we could add some fluoride there. Now, the last thing I'm going to say, and then I'll be done here. This will take like 2 minutes. But is that good? Okay. We want to make sure we're adding something that we can actually, you know, react to something opposite first of all that reacts with this to make sure we get a solid so we can see that happen. Right? If you add something aqueous, you're not going to see anything. Now, last thing. I have a question for you. Let's just focus on this beaker right here, right now. Okay? And I know you're going to give me 2 answers, and that's, well, you're going to give me 1 answer for sure, and that's okay, because this has to happen. What else is in this beaker besides Br minus? What else is in this beaker besides Br minus? So most people would say water, yes? Is there anything else in this beaker? Yes. What? Water? No. What else? And this is the important part you have to understand about this. Think about the last example we did for a second. Same thing here. What else is in this beaker? What does Br minus mean? What does that mean? What does bromide ions mean? Br minus, Br1 minus. What does that mean? Okay, so it's gained an electron. So what do you think I'm going to ask you next? If it gained an electron, the next comment I'm going to, where did it come from? Right? Where did the electron come from? And the answer is it didn't come from water, it came from a metal. Right? So remember, when we talk about ionic compounds, they're compounds. When we talk about ions in water, they come from ionic compounds. That's the only way you can get an ion. There's no such thing. You can't go to the back room. I'm telling you right now, this is important. Listen, you can't go to the back room and grab a bottle and be like, oh, look, I have the bromide ion bottle here. Here's the bromide ions. Because, of course, it's gained an electron. Well, where did the electron come from? There's no such thing as Br minus ions. Okay? The electron has to come from a metal. Right? Ionic compounds. Ions come from ionic compounds. In fact, the only way to get ions is from ionic compounds when you put them into water. There's no such, you can't walk down the street and be like, oh, look, calcium 2+ ions. No. Calcium atoms? Yeah, sure. But you're not going to be like, oh, look, calcium ions, because calcium ions implies that it's lost 2 electrons. The next question I'd ask you is, who took those electrons? A non-metal did. Okay? They have to go together. So when I say Br minus is in here, that's true, but maybe there's some K plus in here as well, okay? Like what I'm interested in is the bromide ion. But I know that K plus and Br minus is very soluble. So yes, there's K pluses in here, and yes, there's Br minuses, and I'm interested in this part. When I add silver ions, can I just add silver ions, go to the back room and grab the silver ions and dump them in? No, I have to do what I did today, which was I have to start with the ionic compound, okay? So maybe I use some silver nitrate here, and the reason I'd use silver nitrate is because it is also very soluble. And then what happens is I dump that in, it breaks into the two ions. Yes, I get some nitrate ions, but yes, I get some silver ions, and that's what I'm interested in, okay? Because this and this are going to create a solid, yes? The other two ions, we're going to learn, we're going to talk about this. Listen, this ion, will it combine with this? Absolutely it will, because they're oppositely charged. But they're also very soluble, so you're not going to see them. We call those ions spectator ions, okay? They're there to watch the reaction take place, okay? And that's all we're going to do for today.